Okay, today we're getting into ideas of dimension and rank. Okay, so dimension is pretty easy. Last class we had a discussion about that if I have a basis, the basis has to have a particular size. So if V is a vector space and B is a basis for V, then the size of the basis is fixed at some number n. Um, then we say that the dimension of B is n. We now have a word for this, right? That we have the dimension of the vector space. So I did an example in the notes there. I said W is some vector space where all the components are D, the vectors have the components D, C minus D, C, and this is in R3, and C and D are both elements of the reals, right? Then if I let S be the space 1, -1, 0, or 0, 1, 1, so this is a set. This is a basis for W, and you can kind of stop and look at that, check it out, but it's going to work. But this implies that the dimension of W is 2, okay? Because I can create every vector that's in W using these other two vectors in linear combination, and I only need two vectors to do it, so the dimension of W in and of itself is 2. Even though it's a subspace of R3, it is only a two-dimensional subspace, so it's a reduction in size. Okay, so we have some basis tests here. We established that one, basically if S is linearly independent and the size of S is equal to the dimension of V, right? Then we also, I guess, we're assuming that S is a subset of V. Then this implies that S is a basis. So this is the criteria of linearly independent and right size. 2 is that if V is equal to the span of S, and the size of S is equal to the dimension of V, then S is a basis, right? So this is the idea that if I have spanning and right size, I get a basis. So spanning and right size gets me a basis. Linear independence and right size gets me a basis. And finally, we also know that linear independence and spanning gets us a basis, because that's the definition of a basis. Okay, so we need some more definitions here. Okay, so we're going to let A be some typical M by N matrix. Okay, so A is A11, A12 out to A1N, A21, A22 out to A2N, down to AM1, AM2 out to AMN, right? So there's my matrix. All right, so if I look at this, the rows themselves, so the vector A11, A12 out to A1N, A21, A22 out to A2N, and then we keep going until we get to AM1, AM2 out to AMN. These are what we call the row vectors of A. And likewise, I can create column vectors, right? So A11, A21, A out to AM1, A12, A22 out to AM2, and then down to A1n, A2n, out to AMN are the column vectors. So these are row vectors, and these are column vectors. Okay, so the rows of A make a set of vectors called the row vectors. The columns of A make a set of vectors that we call the column vectors. Okay, so if you take R, so S is the set of row vectors, and if you span that set and call this R, then we call R the row space of A. If I have T is the set of column vectors, and C is the span of T, then we call T the column space of A. And if you stop and you work this all out, you're going to see that these are vector subspaces, and of Rn or Rm. In some way, you can prove that by showing closure under addition and scalar multiplication. But we're not going to worry too much about that. We're going to get to some things that are interesting about this. Okay, so we get a theorem here that tells me that if A is m by n and B is m by n, and A is row equivalent to B, and RA is the row space of A, and RB is the row space of B, then we know that RA is equal to RB. All right, so proving this is not actually that challenging. If these things are row equivalent, then I can take the rows of B and make linear combinations and get the rows of A. So RA has to be a subset of RB. Likewise, I can take the rows of B or rows of A and make linear combinations to get the rows of B. So RB has to be a subset of RA. If they're subsets of each other, then they have to be the same set. So that's pretty simple. Okay. So the row space, if things are row equivalent, the row space of one is equal to the row space of the other. All right, this gives me another theorem, which tells me that if A is Gauss-Jordan of B, then the non-zero rows of A form a basis for the row space of B. Okay, so if I do Gauss-Jordan, I'm going to get a set of rows, and those rows that I'm left with that are non-zero are the basis for the row space. You can make all of the rows of the original matrix out of the non-zero rows. So let's say I have 1, 3, 1, 3, 0, 1, 2, 0, negative 3, 0, 7, negative 1, 3, 4, 1, 1, 2, 0, negative 2, negative 2. If I RREF that, use Gauss-Jordan, I get 1, 0, 0, negative 2, 0, 1, 0, 2, 0, 0, 1, negative 2, 0, 0, 0, 0, and 0, 0, 0, 0. So the argument here is that these three vectors, 1, 0, 0, negative 2, 0, 1, 0, 2, and 0, 0, 1, negative 2 together make a basis for the row space of B, or of A. So all of the rows that are in A, or anything you can make a linear combination out of those rows, can actually be made by just combining these three vectors. So that's kind of straightforward. You can use a similar method, and I actually put it in the notes, so I'm not going to write it all out here, to find a basis for the column space. That you just take the transpose of A, and then take the non-zero vectors that result from that. Now, you'll see in the notes that if you do that, you're also going to have a basis that has three vectors. So the row space has a basis here that has three vectors. The column space has a basis that has three vectors. And you're going to find that those two numbers are always equal. So this gets us a theorem. And the theorem says that if A is an m by n matrix, right, and I take its row space and I take its column space, then the row space and the column space have the same dimension. And what do we call that number? We're going to call that number the rank. So the rank of the dimension of the row space and the column space of A is what we call the rank of A. And in fact, if you put a matrix into MATLAB and you type rank A, it returns a number. Okay? Okay, so let's let A be 1, negative 2, 0, 1, 2, 1, 5, negative 3, 0, 1, 3, 5, and if I take the reduced row echelon form of that, we get 1, 0, 0, negative 7, 0, 1, 0, negative 4, 0, 0, 1, 3. Well, that says that my row space has three vectors in the basis, so the rank of A is 3. And if I did the column space, I would also get three vectors. And if you note here, the column space is going to have like a blank row there. It's going to have a row with zeros. Okay, so we have one last concept here, and then we're done for the day. And we're going to create a thing that we call the null space. So null just means like equaling 0. So A is going to be an m by n matrix such that X is an element of our n, right? Okay, so n is going to be the set of all X in Rn that solve the system of equations Ax is equal to the 0 vector. Okay, so if it solves the homogeneous system of equations, it is in this set. We call this set the null space. Okay, if I take the dimension of this set, I get a number that I call the nullity. The nullity of the set is the nullity of the matrix is the dimension of the matrice's null space. Okay, so let's take an example of this. Okay, if I take A as 1, 0, negative 2, 1, 3, 1, negative 5, 0, 1, 2, 0, negative 5, then Ax equals 0 is going to be solved by using the augmented matrix 1, 0, negative 2, 1, 0, 3, 1, negative 5, 0, 0, 1, 2, 0, negative 5, 0. If I work with that and I take Gauss-Jordan on that, I'm going to get 1, 0, negative 2, 1, 0, 0, 1, 1, negative 3, 0, 0, 0, 0, 0, 0. All right, so what do we see there? We see that if I let x4 equal t and x3 equal s, then x2 has to be negative t plus 3s, and sorry, x4 is s, that's not correct, and x3 is t. So this one's s, this one's t. Negative 2, all right, so that'll be negative t plus 3s, and x1 should be 2 minus s, which means that I can write any solution to this as s times the vector 1, 0, 3, negative 1. This is 2t. There we go. And plus t times the vector 0, 1, negative 1, 2. So any solution to this is going to be a linear combination of these two vectors. Well, that means that n spans these two vectors, which means the nullity of matrix A should be 2, right? Because I have made a basis for the solutions to the homogeneous system of equations. It has two vectors that I can make all the solutions out of linear combination of those two vectors. Therefore, the nullity of this is 2. Now, if you're paying attention here, the rank of this matrix is going to be also 2. Now, the rank and the nullity are not the same number, but later on we're going to see that there is a way to find the rank from the nullity and the nullity from the rank. And in fact, the nullity plus the rank is going to have to equal the number of columns in the matrix. So we'll see that later on as we move forward. All right, so there we go. Lots of dimension, rank, and we introduced a little bit on nullity here.